All right, let's talk tree diagrams with and without replacement. Here's an example. You can quiz yourself while you're watching. So if you have a bag of counters, 3 blue and 7 red, and you pick out one counter without looking, and you put it back in the bag, then you pick out another counter. What's the probability that you pick out a red counter and a blue counter? So I've started the tree diagram for you. The first thing you have to decide is this an independent or a dependent event? And the key to it is there replacement or is there not replacement? So in this case, it says they put it back in the bag. So that would be with replacement, which would mean these are independent events. Whatever happens the first time I pull the counter out of the bag doesn't affect what I'm going to pull out of the bag on the second draw since I replaced it. So pause this video, try to fill in your tree diagram and compute all the probabilities at the end of the branches, and then write down the probability that you get one red-blue counter and one blue counter in either order. Then start the video again and see if you were correct. All right, did you get the right answer? So since it was with replacement, our probabilities on our second branches do not change from the first branch. Our sample size didn't change because we replaced it. This was an independent event. And notice that if you add up all of these outcomes on this far right, you will get a sum of 1. Okay, because you would get 100 over 100, which would simplify to 1. Now when you answer the actual question of what's the probability that you get one red and one blue counter, and that doesn't say in either order, but if it's not specified, it would mean in either order. So you're going to take these two middle outcomes of RB and BR and add them. 21 over 100 plus 21 over 100 would be 42 over 100, which would simplify to 21 over 50. I hope you got that one right. Now let's try one without replacement. Same scenario, you have 3 blue, 7 red, and you're not going to put it back in the bag after you pull out the first counter and record it. So I got it started for you. The probability that you're going to pull out a red counter on the first draw would be 7 out of 10. But on the second draw, notice that it's only 6 out of 9. And that's because I am not replacing the counter. Okay, so pause the video here. I hope you determined whether it was an independent event or a dependent event, and you can complete the remaining of the tree diagram. Start the video again when you're ready. All right, how'd you do? Again, notice all these denominators are 9s, and that's because there's only 9 counters in the bag. And if we sum all of these, we will get 90 over 90 for a total of 1. Again, we're answering the same question, so it's going to be RB and BR, which would be 21 over 90 this time, plus 21 over 90, which is 42 over 90, which simplifies to 7 over 15. Let's try one more. I place a bet on the outcome of 2 football matches. The probability I win on the first match is 1 out of 10, and the probability I win on the second match is 3 out of 10. Calculate the probability of me winning both of my bets, and then calculate the probability that I win at least one of the bets. After calculating those, start the video again so you can see if you were right. All right. Did you get them? So the probability that it's a win-win is 1 out of 10 times 3 out of 10, which is 3 out of 100. The probability that I win at least one, some of you might have thought it was just win-loss and loss-win, so you might have gotten 34 out of 100, but you forgot that this least means I could win them both. So I have to include that as well. It's only a minimum requirement, not a maximum requirement. So instead of 34 over 100, you would get 37 over 100. I hope that was a nice way to quiz yourself so you could see if you were right and if you're getting the hang of tree diagrams and with and without replacement, independent versus dependent events.